STEM science.
Ah, yes, the sun. Although you can't really see it right now, it is there, and we enjoy the light from it, hence daylight right now. And as we enjoy this daylight, it's important for us to reflect on the fact that there are a series of complex nuclear reactions taking place right now. And it's because of those nuclear reactions, nuclear fusion, that we actually have stuff like carbon, uh, iron, aluminum, all of these elements that we see all around us. Well, it's all because of what's happening in that star, plus many other larger stars. And we'll talk about that coming up. First of all, let's just remind ourselves of what this is all about. So the periodic table of the elements basically lists off all of the known elements that we know of here on Earth. And it starts off with the first one, hydrogen. So if we were to take a look at the hydrogen atom, or the element with the atomic number of 1, we would see that in the nucleus we would have 1 proton, hence the atomic number 1, as well as 1 electron. The next element in the periodic table takes us to atomic number 2, or 2 protons in the nucleus. That gives us helium. And you get the idea. The next one up is lithium, 3 protons, or an atomic number of 3 on our periodic table. And that's really the pattern that we see here in the periodic table. As we move up in atomic number, that just means we have more and more protons in the nucleus of the atom. And the atoms get bigger and bigger and bigger. So how are these different elements connected to stars? Well, the answer is in the life cycles of stars. Well, stars are created in these vast clouds of hydrogen. Here we see one of those. It's called a nebula. And this brings us back to one of the key parts in particle theory, which is that particles are attracted to each other. And in the vacuum of space, these particles, these atoms of hydrogen, will start to attract each other, and they will begin to collect, and they will begin to pull each other closer and closer and closer. As these clusters of hydrogen begin to pull each other closer and closer, that just increases the pull of other hydrogen particles, until finally it generates enough heat that it's actually able to ignite. This is the birth of a star. And in fact, the heat energy is so intense, so strong, that it actually is enough to cause hydrogen atoms to fuse. This is nuclear fusion. Hydrogen atoms begin to fuse with each other to create heavier atoms. And in this case, 2 hydrogen atoms fuse to create helium. As these hydrogen atoms fuse through nuclear fusion, it releases an incredible amount of energy. This energy goes on to cause other atoms of hydrogen to fuse and form helium. It is also these reactions and this incredible release of energy that really gives us the energy, the luminosity that we associate with stars. Now, this doesn't end there. More and more of these hydrogen atoms, and now these other heavier helium atoms, begin to fuse to create even larger and larger atoms, larger and larger elements. Beryllium, nitrogen, carbon. These are these larger and bigger elements that are now created inside of these stars through nuclear fusion. And thanks to these nuclear fusion reactions that are taking place in stars, we begin to fill out the periodic table. Lithium, beryllium, boron, nitrogen, oxygen. All of these elements are the products of nuclear fusion that took place in stars. The fusing of the different nuclei of atoms forming larger and larger atoms. But something changes when we get to iron. In a star, after nuclear fusion, iron is an element that does not tend to release a lot of energy. In fact, it absorbs a lot of energy, and as a result, does not produce a lot of energy to go on to power more fusion reactions. And as a result, as a star ages and continues to burn, it starts to collect and generate a core of iron. And this iron does not go on to fuse to form more and more heavier elements. It actually just continues to build inside of a star. This is the starting stages leading to the death of a star. So if nuclear fusion within a star is incapable of creating heavier elements past iron, where do these larger elements come from? For this, we need to focus not on average size stars, but on these much larger massive stars. Even within a massive star, iron continues to build inside at its core. As this iron core within this massive star continues to grow, it continues to pull in on itself. Don't forget, gravity is still at work. These particles of iron continue to attract each other. This iron core continues to pull in on itself, and because, again, it is unable to undergo nuclear fusion, at some point, this increase in pressure and energy is finally released as a huge supernova, an explosion. It is the energy created within this supernova, this giant explosion, that then allows the fusion of these heavier iron atoms to now begin to fuse with each other. And as a result, it is here where the heavier elements beyond iron are created. So looking back at our periodic table, starting with hydrogen, elements after hydrogen going up all the way to iron, atomic number 26, these elements are really created through nuclear fusion reactions taking place within stars. The larger or heavier elements after iron are really the result of elements that were created from supernova explosions. These massive stars that are exploding and releasing even more energy that go on to fuse these larger and larger atoms together. So think about it. All the different materials that you see around you today, right now, the different metals, the gases that you're breathing in right now, the materials that you're eating, the stuff that makes up you, these atoms, these elements are really the byproducts of the nuclear reactions that are taking place within stars, as well as the nuclear reactions that take place that are powered through the explosion of these massive stars.